Our journey begins in the unfathomable depths of time, long before the existence of our sun, our planet, or even the familiar stars that now fill our night sky. Imagine a universe in its infancy, a vast and silent expanse where only the faintest wisps of hydrogen and helium drifted through the darkness. Roughly 4.6 billion years ago, within one of the spiral arms of our galaxy, a dense region of a giant molecular cloud began to collapse under its own gravity. This nebula, rich in elements forged by generations of earlier stars, twisted and churned as shockwaves from nearby supernovae rippled through its depths, compressing the gas and dust ever tighter. Over millions of years, gravity sculpted this cloud into a spinning disk, its center growing ever denser and hotter as material spiraled inward. At the heart of this maelstrom, nuclear fusion ignited, birthing a new star, our sun, whose fierce radiation began to sweep away the remaining gas and dust. In the swirling disk around the newborn sun, countless grains of rock and ice collided, sticking together to form larger and larger bodies called planetesimals. Through relentless bombardment and merging, one of these planetesimals grew larger than the rest, destined to become the early Earth. The young planet endured a relentless barrage of impacts, each collision releasing tremendous energy, melting rock and reshaping its surface. In these early eons, Earth was a seething sphere of molten rock, its surface a hellish landscape of lava oceans and erupting fissures. Towering volcanoes erupted ceaselessly, releasing plumes of sulphurous gases and thick clouds of ash into the turbulent sky. The atmosphere was a dense, choking mixture of carbon dioxide, methane, ammonia, and water vapor, utterly inhospitable to any form of life. Sunlight struggled to penetrate the thick haze, casting a dim, ruddy glow over a world devoid of blue skies or gentle breezes. For hundreds of millions of years, Earth's surface was a desolate wasteland, sculpted by relentless volcanic activity and battered by cosmic debris. Asteroids and comets, remnants from the solar system's chaotic birth, rained down in a cataclysmic bombardment, delivering both destruction and vital ingredients for the future. Among these collisions, one event stands out, a titanic impact with a Mars-sized body known as Theia. The force of this collision vaporized vast portions of Earth's crust and mantle, hurling molten debris into orbit and forever altering the planet's destiny. Over time, this ring of incandescent fragments coalesced, giving birth to our moon, a silent companion that would shape tides and stabilize Earth's rotation. As eons passed, Earth's surface began to cool, the relentless heat radiating into space, allowing a thin crust to form atop the still molten interior. This crust, fragile and fractured, floated atop a restless sea of magma, shifting and buckling as the planet continued to lose heat. As temperatures dropped further, water vapor in the atmosphere began to condense, forming dense clouds that blanketed the planet. Torrential rains fell for millions of years, carving channels into the raw volcanic landscape and cooling the surface with every drop. These relentless storms filled the planet's vast basins and craters, gradually giving rise to the first primordial oceans. The newborn seas were dark and mineral-laden, their surfaces whipped by fierce winds and illuminated only by the occasional flash of volcanic lightning. These waters, though devoid of life, were the crucible in which the building blocks of biology would one day assemble. The early Earth was a world in constant flux, its surface reshaped by volcanic eruptions, shifting plates, and the ceaseless interplay of fire and water. The crust fractured into immense plates, which drifted atop the viscous mantle, colliding, rifting, and grinding past one another in a slow, relentless dance. These tectonic forces built towering mountain ranges, opened vast rift valleys, and recycled the planet's crust in a never-ending cycle of creation and destruction. Over billions of years, the restless movement of these plates would assemble and break apart supercontinents, shaping the face of the planet again and again. Names like Rodinia and Pannotia mark epochs when landmasses larger than any today dominated the globe, only to fragment and disperse as the planet evolved. These supercontinents, barren and windswept, were bordered by deep oceanic trenches and ringed by chains of volcanoes, their surfaces shaped by the relentless forces of geology. In the shadowy depths of these ancient oceans, volcanic vents spewed superheated, mineral-laden water, setting the stage for the extraordinary emergence of life, a story that would unfold in the eons to come, driven by the ceaseless dynamism of our ever-changing planet. For hundreds of millions of years, the newly formed oceans stretched endlessly, their surfaces shimmering beneath alien skies, yet their depths remained devoid of life. These waters were a swirling mixture of minerals and dissolved gases, constantly replenished by volcanic eruptions and the relentless churning of the planet's crust. Far below the surface, hydrothermal vents spewed scalding water and chemicals into the abyss, creating pockets of warmth and energy in the otherwise cold, dark ocean. In these dynamic environments, simple molecules collided and fused, driven by heat and mineral catalysts, gradually assembling into more complex organic compounds. Around 3.7 billion years ago, the first primitive cells emerged, tiny membrane-bound bubbles capable of harnessing energy and replicating themselves. These earliest life forms, known as prokaryotes, floated freely in the water, absorbing nutrients and multiplying in the mineral-rich soup. They were the ancestors of all future life, their simple structures containing the blueprints for evolution's endless possibilities. At first, these cells were little more than fragile sacks of chemicals lacking specialized parts or complex behaviors. They had no senses, no ability to move with purpose, and no defenses against the shifting tides or chemical changes around them. Their existence revolved around absorbing dissolved nutrients and dividing, each generation nearly identical to the last. For over 1 billion years, these simple cells dominated the oceans, forming invisible clouds of life, drifting through the water. The ocean was a silent world, its only inhabitants these microscopic pioneers living in the gentle currents and shadows. On land, the scene was starkly different, bare rock and dust, untouched by life beneath a thick, orange-tinged atmosphere. But beneath the waves, life began to diversify. Some cells developed thicker membranes, others evolved the ability to store energy more efficiently, and a few even formed protective coatings to survive harsh conditions. The ancient oceans were murky and dense with minerals, their chemistry constantly shifting as volcanic activity and meteor impacts altered the environment. With almost no oxygen in the air or water, these organisms relied on chemical reactions, chemosynthesis, to extract energy from sulfur and iron compounds near the vents. Some cells clustered around hydrothermal vents, thriving on the chemical-rich plumes, while others adapted to the open ocean, feeding on whatever nutrients drifted their way. In the darkness, these microbes formed the foundation of the first food webs, their slow, random movements shaping the earliest ecological interactions. Life was precarious. Sudden changes in temperature, chemistry, or pressure could wipe out entire populations, but the survivors adapted, passing on traits that made them more resilient. Over time, some cells developed the ability to repair their membranes, others evolved to withstand extreme heat or acidity, and a few began to cooperate, forming loose colonies for mutual protection. These colonies marked the first steps toward complexity, as cells communicated chemically and shared resources, slowly altering the chemistry of the oceans around them. For eons, the oceans remained a realm of single-celled life, but within this apparent simplicity, a hidden world of diversity was unfolding. Some cells evolved flagella, tiny whip-like tails, to propel themselves through the water, while others developed the ability to sense light or chemicals, guiding them toward food or away from danger. Evolution was relentless, mutations accumulated, and new forms emerged, cells with internal compartments, cells that could photosynthesize, and cells that preyed on others. Each adaptation, each tiny innovation, allowed life to exploit new niches, setting the stage for the rise of more complex organisms. Without these countless generations of microscopic pioneers evolving and interacting in the ancient oceans, Earth would have remained a barren, lifeless world adrift in the cosmos. For over 1 billion years, Earth's biosphere was dominated by simple, single-celled organisms. These ancient microbes thrived in a world devoid of oxygen, inhabiting the planet's vast primordial oceans and shallow pools. Life's slow evolutionary pace was about to accelerate. A remarkable innovation emerged. A new lineage of bacteria capable of transforming sunlight into energy. Roughly 2.4 billion years ago, cyanobacteria, sometimes called blue-green algae, evolved the ability to perform oxygenic photosynthesis, a process that would forever alter the planet's destiny. Harnessing sunlight, these microorganisms split water molecules, using the hydrogen to build organic compounds and releasing oxygen as a byproduct. This oxygen, once a rare trace gas, began to accumulate in the oceans, saturating the water and eventually escaping into the atmosphere. For millions of years, oxygen produced by cyanobacteria reacted with dissolved iron and other elements, forming vast deposits of banded ironstone on the ocean floor, a geological signature of this transformation. Eventually, the oxygen sinks became saturated, and free oxygen began to accumulate in the atmosphere. This pivotal moment is known as the Great Oxygenation event. For most existing life, oxygen was a lethal threat. Anaerobic organisms, adapted to an oxygen-free world, found themselves exposed to a highly reactive and toxic gas. Massive die-offs swept through microbial communities. Oxygen's corrosive properties damaged cellular machinery, leading to one of Earth's earliest and most profound extinction events. Entire populations of anaerobic bacteria perished, unable to adapt to the new oxygen-rich conditions. The biosphere was reshaped, and only the most resilient or adaptable species survived. Yet life's tenacity prevailed. Some microorganisms evolved protective enzymes, such as catalase and superoxide dismutase, to neutralize oxygen's harmful effects. A few lineages went further, developing metabolic pathways that used oxygen for respiration, a far more efficient way to extract energy from nutrients. Aerobic respiration allowed these organisms to grow larger, move faster, and exploit new ecological niches, setting the stage for biological complexity. The environmental consequences were equally dramatic. As atmospheric oxygen increased, it reacted with methane, a potent greenhouse gas, triggering a catastrophic drop in global temperatures. Earth entered a period of extreme glaciation, known as Snowball Earth. Ice sheets may have stretched from pole to pole, encasing the planet in a frozen shell. For millions of years, sunlight reflected off the icy surface, and temperatures plummeted. Life was forced to retreat to isolated refuges such as hydrothermal vents and geothermal springs. In these hidden sanctuaries, extremophiles endured, relying on chemical energy from Earth's interior rather than sunlight. The Great Oxygenation event stands as a testament to life's power to reshape its environment. Cyanobacteria, through their relentless photosynthesis, transformed the chemistry of oceans and air. Over time, these microbial pioneers paved the way for new forms of life, fundamentally altering the trajectory of evolution. As the planet slowly warmed and the ice receded, oxygen levels continued to rise, creating an environment ripe for innovation. The abundance of oxygen enabled the evolution of eukaryotic cells, organisms with complex internal structures and specialized compartments. Eventually, some of these cells began to cooperate, forming the first multicellular organisms. This leap in complexity allowed for division of labor and the emergence of specialized tissues. Multicellularity opened the door to an explosion of diversity, as organisms adapted to fill new ecological roles. Cells could now specialize for movement, feeding, defense, or reproduction, leading to increasingly intricate life forms. The groundwork was laid for the rise of animals, plants, and fungi, every complex organism that would ever inhabit the planet. The very air we breathe is a legacy of the great oxygenation event, a profound turning point driven by the smallest architects of change, cyanobacteria, whose impact echoes through every breath of life on Earth. After the Earth thawed from its deep freeze, life began to diversify in astonishing ways, filling every available niche with new and remarkable forms. We enter the Carboniferous period, beginning around 359 million years ago, a time when the world was transformed by lush, sprawling forests and a climate that fostered extraordinary life. Vast, swampy forests blanketed the land, their canopies thick with moisture and shadows, creating a humid, oxygen-rich environment. Unlike the forests of today, these ancient woodlands lacked flowers and fruit. Instead, they were dominated by primitive plants, towering ferns, club mosses, and horsetails, stretching skyward in dense, tangled masses. Some of these plants reached heights of over 30 meters, their thick stems and fronds forming a living labyrinth across the landscape. When these giants died, their remains fell into the stagnant waters below, where decay was slow and incomplete, preserving vast quantities of organic material. Over millions of years, these layers of plant matter were buried and compressed, eventually forming the immense coal beds that would one day power civilizations. This is why the era is called the Carboniferous, the coal-bearing period, a testament to the sheer abundance of plant life. These forests did more than shape the land. They transformed the very air, releasing vast amounts of oxygen through relentless photosynthesis. Sunlight filtered through the dense canopy, fueling a green engine that pumped oxygen into the atmosphere at unprecedented rates. Oxygen levels soared to as high as 35%, far above the 21% of today, creating an environment unlike any before or since. In this oxygen-rich world, insects and other arthropods underwent a dramatic transformation, evolving into giants that dwarfed their modern relatives. Unlike vertebrates, insects lack lungs. Instead, they rely on a network of tiny tubes, tracheae, that branch throughout their bodies, delivering oxygen directly to their tissues. This system works efficiently only when oxygen is abundant, and in the Carboniferous, it allowed insects to reach astonishing sizes. The size of an insect is limited by how much oxygen it can absorb, and with so much oxygen in the air, the upper limit was pushed to extremes. The forests teemed with enormous arthropods, creatures that would seem monstrous by today's standards. Dragonflies with wingspans rivaling modern birds darted through the humid air, while colossal millipedes and armored scorpions prowled the forest floor. Meganeura, the largest known dragonfly, soared above the swamps, its wings stretching over 75 centimeters, its flight silent but commanding, a master of the Carboniferous skies. On the ground, Arthropleura, a millipede as long as a small car, slid through the undergrowth, its segmented body armored and flexible, feeding on decaying plant matter and shaping the forest floor. Giant scorpions, some nearly a meter in length, hunted in the leaf litter, while enormous cockroaches scuttled through the shadows, thriving in the damp, decaying world. In this era, insects and their kin were among the dominant land animals, their numbers and diversity unmatched. These creatures were not simply scaled-up versions of modern insects. Their bodies were adapted to the unique challenges of their world. Thick exoskeletons protected them from predators and the elements, while specialized limbs and mouthparts allowed them to exploit a variety of food sources. Some, like the giant dragonflies, were agile aerial hunters, preying on smaller insects and even early amphibians. Others, such as the massive millipedes, were detritivores, breaking down fallen plant matter and recycling nutrients back into the ecosystem. These were the first giants to walk the land. their movements shaping the environment and influencing the evolution of other life forms. Their senses were finely tuned to their world. Compound eyes provided a wide field of vision, while long, sensitive antennae detected subtle changes in humidity, temperature, and the scent of prey or mates. Interactions among these giants were complex. Predators stalked prey through the dense foliage, while rivals competed for territory and mates. Some species developed elaborate courtship displays, waving their massive limbs or vibrating their wings to attract partners. Reproduction was a crucial part of their life cycle. Many laid eggs in moist soil or decaying wood, where larvae would hatch and feed, growing rapidly in the nutrient-rich environment. Some, like the dragonflies, began life as aquatic nymphs, fierce predators in ancient ponds and streams, before emerging as adults to dominate the air. Yet the reign of the giant insects was not eternal. As the Carboniferous drew to a close, the climate shifted. Rainforests began to shrink, fragmented by cooler, drier conditions. The once continuous canopy broke apart, and the swamps receded. The planet's surface dried, and the vast wetlands that had nurtured these giants vanished. With fewer plants, atmospheric oxygen levels began to fall, returning closer to modern values. For the giant insects, this was catastrophic. Their massive bodies, once perfectly suited to a super-oxygenated world, now struggled to survive. Their tracheal systems could no longer deliver enough oxygen, and their populations dwindled. Unable to adapt to the new world, these titans faded from the land, leaving only their fossils as evidence of their former glory. In their absence, new forms of life emerged, smaller, more adaptable animals that would shape the next chapters of Earth's history. The story of the giant insects is a vivid reminder of how life and environment are inseparably linked, each shaping the other in a dance that continues to this day. After the age of giant insects, the world entered a new era, one defined by the rise of the reptiles. As lush forests and sprawling swamps gave way to more open landscapes, early reptiles began to diversify, adapting to a wide range of environments. Among these pioneering creatures, the archosaurs emerged as a dominant lineage, setting the stage for the most extraordinary chapter in Earth's history, the reign of the dinosaurs. Reptiles, with their scaly skin and efficient lungs, thrived in the increasingly dry and variable climates of the Triassic period. Archosaurs, a group that included not only dinosaurs but also the ancestors of crocodiles and pterosaurs, evolved remarkable adaptations. Some developed upright postures, allowing them to move swiftly and efficiently across vast floodplains and fern-filled valleys. Dinosaurs first appeared around 230 million years ago, small and nimble at first, but soon radiating into an astonishing array of forms. Over the next 150 million years, they would become the undisputed rulers of the land, filling every ecological niche from towering herbivores to agile predators. The Mesozoic era, often called the Age of Dinosaurs, was a time of dramatic change. Earth's continents slowly drifted apart, reshaping coastlines and creating new habitats. Volcanic eruptions and shifting climates forced life to adapt, and the dinosaurs responded with an explosion of diversity. In the Jurassic period, the world was dominated by immense forests of conifers and cycads, where herds of sauropods, giant, long-necked plant-eaters, roamed in search of food. These titans, like Brachiosaurus and Diplodocus, could strip entire trees bare with their sweeping necks, their massive bodies supported by pillar-like legs. Moving in groups, they likely communicated with deep, resonant calls that echoed across the valleys. The presence of such enormous herbivores shaped the landscape itself. Their constant grazing opened up clearings in the forests, creating new opportunities for smaller dinosaurs and other animals. The ground shook beneath their weight, and their migration patterns may have influenced the growth of prehistoric vegetation. But where there are giants, there are also hunters. Apex predators like Allosaurus stalked the herds, relying on keen senses and powerful jaws to bring down prey. These carnivores were not mindless killers. They may have hunted in coordinated groups, using strategy and speed to outmaneuver their massive targets. Their sharp teeth and strong limbs made them formidable opponents in the eternal struggle for survival. Above, the skies teemed with life. Pterosaurs, the first vertebrates to achieve powered flight, soared on leathery wings, scanning the ground for fish, insects, or small dinosaurs. Some species, like Quetzalcoatlus, reached wingspans rivaling small airplanes, gliding effortlessly over ancient rivers and coastal lagoons. As the supercontinent Pangaea began to fragment, new coastlines and isolated landmasses emerged. This geographic upheaval drove evolutionary innovation as populations became separated and adapted to unique climates and resources. Dinosaurs evolved into a dazzling variety of forms: armored Ankylosaurus with its club tail, horned Triceratops defending itself with massive frills, and swift, feathered velociraptors darting through undergrowth in coordinated packs. The Cretaceous period saw the rise of flowering plants, transforming the landscape and providing new food sources for herbivores. Dinosaurs responded with specialized teeth and digestive systems, allowing them to exploit these resources. Herds of hadrosaurs, or duck-billed dinosaurs, grazed in vast numbers, their social behaviors and vocalizations hinting at complex group dynamics. Among the most iconic of all was Tyrannosaurus rex, a predator of immense power and intelligence. Standing over 3.7 meters tall at the hips and stretching up to 12 meters in length, T-Rex was equipped with bone-crushing jaws and acute senses. It likely hunted both alone and opportunistically, scavenging carcasses and asserting dominance over its territory. Yet the world of the dinosaurs was not just about size and strength. Many species displayed intricate behaviors. Some built nests and cared for their young, while others migrated across continents in search of food and favorable climates. The fossil record reveals evidence of social interaction, cooperation, and even possible communication through vocalizations and displays. Dinosaurs adapted to nearly every environment on the planet. From the dense forests of the Jurassic to the arid deserts and coastal plains of the Cretaceous, they thrived in swamps, woodlands, and open grasslands. Their evolutionary success was matched by their diversity, ranging from tiny bird-like Microraptor gliding between trees to the armored giants and horned behemoths that defended themselves with spikes, plates, and horns. For 150 million years, these titanic creatures shaped the world around them. Their presence influenced the evolution of plants, the distribution of other animals, and even the chemistry of the atmosphere. The age of giant reptiles was a time of relentless change, adaptation, and innovation, a testament to the power of evolution and the resilience of life on a dynamic planet. Their reign, measured in millions of years, dwarfs the entire span of human history. The world of the dinosaurs was not a static tableau, but a living, breathing ecosystem, filled with drama, competition, and constant transformation. In this world of titans, every day was a struggle for survival, and every adaptation was a step toward the future of life on Earth. The history of life on Earth is a saga marked not by steady progress, but by dramatic upheavals and sudden, catastrophic setbacks. Throughout deep time, the planet has witnessed several mass extinction events, moments when the diversity of life was slashed in a geological instant, forever altering the course of evolution. These were not minor disturbances, but global crises triggered by forces far beyond the control of any living thing. Each extinction event was unique, shaped by a complex interplay of environmental catastrophes. In some cases, volcanic eruptions darkened the skies and poisoned the air. In others, sudden climate shifts or the impact of extraterrestrial objects devastated entire ecosystems. The result was always the same: a staggering loss of life, with entire branches of the evolutionary tree pruned away in a matter of millennia or less. Paleontologists have uncovered the evidence of these ancient tragedies in fossil beds, packed with the remains of vanished species, silent witnesses to the planet's most desperate hours. The most devastating of all was the Permian-Triassic extinction, which struck about 252 million years ago. This event, known as the Great Dying, was triggered by relentless volcanic activity in what is now Siberia. For hundreds of thousands of years, volcanoes erupted continuously, releasing vast quantities of carbon dioxide and methane. These greenhouse gases trapped heat, driving global temperatures to lethal extremes. The skies filled with ash and toxic fumes, blocking sunlight and disrupting photosynthesis. Acid rains scoured the land, while the oceans absorbed carbon, turning acidic and suffocating marine life. The devastation was nearly total. Forests withered, rivers ran lifeless, and the air itself became a hazard. On land and in the sea, entire ecosystems collapsed. The oceans, once teeming with life, became stagnant and depleted of oxygen. Acidic waters dissolved shells and coral, while toxic gases suffocated fish and invertebrates. From space, Earth would have appeared shrouded in a veil of volcanic clouds, its surface scarred by fire and flood, a planet in crisis. Scientists estimate that over 90% of marine species and 70% of terrestrial vertebrates vanished. The biosphere was reduced to a shadow of its former self. For millions of years, the world remained a barren wasteland, with only the hardiest survivors clinging to existence in isolated refuges. Recovery was slow and uncertain. Life had to reinvent itself, evolving new forms and strategies to cope with the altered world. The extinction cleared ecological space, allowing new groups, like the earliest dinosaurs and mammals, to emerge and diversify, setting the stage for future evolutionary dramas. Yet even the mighty dinosaurs, who would come to dominate the planet, were not immune to disaster. The Cretaceous-Paleogene extinction, 66 million years ago, brought their reign to a sudden and violent end. This time, the culprit was a colossal asteroid, hurtling toward Earth at unimaginable speed. Its impact near the Yucatan Peninsula unleashed energy equivalent to billions of atomic bombs. The explosion vaporized everything for hundreds of kilometers, sending shockwaves around the globe and igniting wildfires that raged across continents. Tsunamis swept over coastlines, while a dense cloud of dust and soot blotted out the sun, plunging the world into darkness and halting photosynthesis for months or even years. Temperatures plummeted, and a prolonged impact winter gripped the globe. Plants withered, and the food web unraveled from the bottom up. Herbivores starved, followed by the carnivores that depended on them. The collapse was swift and merciless. In the aftermath, the once thriving dinosaurs and countless other species disappeared, leaving only their bones as a testament to their former glory. The world's great reptilian rulers were gone. Their era ended in a geological heartbeat. The skies and seas, once filled with pterosaurs and giant marine reptiles, grew silent. Even the ancestors of the mighty megalodon vanished. But extinction was never absolute. Survival depended on adaptability. Small mammals and reptiles, able to seek shelter underground or subsist on limited resources, endured where giants could not. Burrowing offered protection from fire, cold, and toxic fallout. Some creatures survived by eating seeds, roots, or carrion, anything that could sustain them through the darkness. Among the survivors were shrew-like mammals and small, feathered dinosaurs, ancestors of today's birds, whose size, diet, and behavior gave them a crucial edge. In time, these survivors flourished, radiating into new forms and filling the empty niches left behind. Each mass extinction, while devastating, became a crucible for innovation, shaping the ever-changing tapestry of life on Earth. With the disappearance of the giant dinosaurs, Earth entered a period of profound transformation. The catastrophic event that ended their reign left behind a shattered world, its ecosystems in disarray and its ecological niches wide open. Into this void stepped the mammals, small, warm-blooded, and covered in fur. For millions of years, they had survived in the shadows, mostly nocturnal, relying on keen senses of smell and hearing to avoid predators and find food in the darkness. Now, with the dominant reptiles gone, mammals began to explore new opportunities. Some ventured into the daylight, evolving adaptations to cope with the sun's heat and the challenges of open terrain. Their fur provided insulation, while sweat glands helped regulate body temperature, allowing them to thrive in a variety of climates. The evolutionary potential of mammals was unleashed. Like a river breaking through a dam, they diversified rapidly, filling roles left vacant by the vanished dinosaurs. Some became swift runners, others powerful diggers, and many developed specialized teeth for eating everything from insects to tough vegetation. Mammals conquered every environment. Some returned to the water, their limbs transforming into flippers as they evolved into the ancestors of whales and dolphins. Others took to the air, their forelimbs stretching into wings, giving rise to bats, the only mammals capable of true flight. On land, mammals grew to impressive sizes. Herbivores like Paraceratherium, the largest land mammal ever, browsed on treetops, while Megatherium, the giant ground sloth, lumbered through ancient forests. Carnivorous mammals, such as the saber-toothed Smilodon, developed formidable weapons, elongated canine teeth and powerful forelimbs to hunt the new megafauna. Mammals adapted to every available niche. Some became burrowers, digging elaborate tunnels to escape predators and harsh weather. Others evolved into agile climbers, their flexible limbs and grasping hands perfect for life in the trees. Early primates, for example, developed forward-facing eyes for depth perception and dexterous fingers for grasping branches and food. These tree-dwelling mammals became increasingly specialized. Some, like the ancestors of lemurs, leapt between branches, while others developed prehensile tails or padded feet for silent movement through the canopy. Their social behaviors grew more complex, with vocalizations and grooming rituals strengthening group bonds. As climates shifted and forests gave way to open grasslands, some mammals adapted to new challenges. Grazers developed high-crowned teeth to process tough grasses, while predators evolved speed and endurance to chase prey across vast plains. Mammals like horses, antelope, and large cats became icons of these new environments. Mammalian brains grew larger and more complex, supporting advanced behaviors such as problem-solving, tool use, and intricate social structures. Some species formed herds or packs, cooperating for defense and hunting, while others developed solitary lifestyles, relying on stealth and cunning. The age of mammals was marked by constant innovation. Marsupials flourished in isolated continents, evolving into unique forms like saber-toothed predators and giant kangaroos. Monotremes, the egg-laying mammals, persisted in Australia, showcasing the diversity of mammalian reproductive strategies. Across the globe, mammals adapted to deserts, mountains, wetlands, and polar regions. Some developed thick fur and layers of fat to survive freezing temperatures, while others evolved water-conserving kidneys and nocturnal habits to endure arid environments. The rise of mammals was a story of resilience and adaptability. Through countless generations, they experimented with new forms, behaviors, and lifestyles, ultimately becoming the dominant animals on land, in the air, and in the water. Their evolutionary journey shaped the world we know today, filling it with an astonishing variety of life. Throughout Earth's history, transformation has been the rule, not the exception. Continents have wandered, climates have shifted, and life has been shaped by upheaval and renewal. But imagine a world where none of this ever happened. The continents remain locked in their primordial embrace, volcanoes lie dormant, and the skies are forever free of catastrophic impacts. In this alternate reality, extinction events never sweep the globe. The same ancient forests, swamps, and shallow seas persist undisturbed for eons. Life, once established, finds itself in a world of endless equilibrium. The environment offers no new challenges, no sudden disasters, no shifting landscapes to force adaptation. In this world, the lush forests of the Carboniferous remain untouched, their towering lycopsids and ferns forming a green canopy that stretches unbroken across the supercontinent. The climate is perpetually warm and humid, with no ice ages to challenge the dominance of ancient plant life. Rivers meander through the same courses for millions of years, and shallow seas teem with the same species generation after generation. Evolution, in this scenario, slows to a crawl. The creatures that first mastered their environments remain virtually unchanged, their forms perfected for a world that never asks them to adapt. The great amphibians of the Permian, for example, continue to dominate the waterways, their bodies unchanged by time. Reptiles, having found their niche, persist in familiar forms. The earliest dinosaurs, never challenged by new predators or environmental shifts, remain the rulers of the land. Mammals, small and nocturnal, never receive the opportunity to expand. Without the extinction of dominant reptiles, they remain in the shadows, their evolutionary potential forever limited. In the dense, unchanging forests, small insectivorous mammals scurry through the undergrowth, their forms barely altered from their earliest ancestors. The absence of mass extinctions means that dominant groups never relinquish their hold. Dinosaurs, unchallenged, continue to diversify only within narrow ecological boundaries. Giant sauropods graze the endless forests, while armored ankylosaurs and swift raptors patrol the undergrowth, their lineages stretching back unbroken for tens of millions of years. The oceans, too, are ruled by ancient dynasties. Marine reptiles like ichthyosaurs and plesiosaurs, never threatened by environmental collapse, remain the apex predators of the seas. Coral reefs, undisturbed by temperature swings or sea level changes, host the same species for countless generations. The evolutionary arms race slows, with little incentive for innovation. Migration patterns remain fixed, as climates never force animals to seek new territories. The same herds follow the same ancient trails, year after year, century after century. New species arise only through slow, gradual changes, minor variations accumulating over immense spans of time rather than bursts of rapid evolution. The most successful forms become living fossils, their bodies so well suited to their stable world that natural selection has little to act upon. Tyrannosaurus-like predators continue to stalk the forests, their reign unbroken by disaster or competition. Giant sauropods browse the treetops, their massive forms unchanged, their dominance unchallenged. The landscape is a living tableau of the Mesozoic, a world where time seems to stand still. In the swamps, ancient amphibians and crocodile-like reptiles continue their slow, patient hunt, unchanged for millions of years. In the oceans, the megalodon and its kin never face extinction. Their massive forms glide through the water, apex predators in a sea that never cools or recedes. Titanoboa, the colossal serpent, continues to haunt the steamy swamps, its size unchecked by environmental change. The world is dominated by giants, reptiles, sharks, and amphibians, each lineage persisting in its ancient form, their evolutionary stories frozen in time. This is a world of remarkable stability, but also of profound evolutionary inertia. The tapestry of life is rich, yet its patterns never change. In this alternate Earth, the drama of adaptation and innovation is replaced by the quiet persistence of ancient forms. The world is familiar, yet forever alien, a testament to the power of change and to the strange beauty of a planet where nothing ever does. Across the surface of the planet, the evidence of transformation is unmistakable. Forests that once stretched unbroken for thousands of kilometers now appear as fragmented mosaics, their edges frayed and interiors thinned. Rivers, once wild and meandering, have been straightened, dammed, and redirected, their ancient courses lost beneath reservoirs and concrete embankments. Mountain valleys echo with the memory of glaciers, now receding at unprecedented rates, leaving behind raw stone and newborn lakes. The air above distant plains shimmers with heat, dust rising from soils stripped of their native cover. Where wild grasslands once rolled to the horizon, geometric patterns of cultivation now dominate, the land divided into grids of monoculture. Wetlands, the lungs of the continents, have been drained and filled, their waters replaced by fields and roads. At night, the planet glows with artificial constellations, clusters of light marking the spread of settlements and industry. The darkness that once blanketed vast regions is now pierced by the steady pulse of electric illumination, visible even from orbit. In the oceans, coral reefs bleach and crumble beneath warming waters, their vibrant communities fading into silence. Dead zones expand where rivers deliver a burden of nutrients and pollutants, suffocating life in once rich coastal shallows. The chemistry of the atmosphere and seas is shifting. Carbon dioxide, released from the combustion of ancient carbon stores, accumulates in the air and dissolves into the oceans, making waters more acidic and altering the balance of marine life. On land, the advance of invasive species disrupts ancient relationships, outcompeting native plants and animals. Habitats shrink and fragment, leaving isolated pockets of life struggling to adapt. The rings of old trees record abrupt changes, years of drought, sudden floods, and the intrusion of pollutants. Canyons and riverbanks reveal layers of sediment, each marking a chapter of accelerated erosion and deposition. The climate itself grows more unpredictable. Storms intensify, droughts lengthen, and the rhythm of the seasons falters. Flowers bloom out of time, and migratory birds arrive to find their feeding grounds transformed or gone. Across the continents, the silence of vanished species lingers. Fossilized remains in exposed earth tell of creatures that once thrived, now lost to the accelerating pace of change. Even the most remote wilderness bears the imprint of distant activity. Microplastics drift on ocean currents, settling in the deepest trenches. Airborne particles circle the globe, falling with the rain onto forests, tundra, and ice. The boundaries of deserts shift, encroaching on fertile lands. Rivers run dry before reaching the sea, their deltas shrinking and salt creeping inland. In the aftermath of wildfires, blackened forests stand as stark reminders of altered cycles. New growth emerges, but the composition of life is changed, some species unable to return. The interconnectedness of climate, water, and living systems is revealed in every altered landscape. The loss of pollinators disrupts the flowering of plants. The decline of forests changes rainfall patterns far away. The story of the planet is now written in the language of transformation, of landscapes reshaped, cycles interrupted, and balances tipped. The consequences ripple outward, touching every ecosystem, every current, every breath of wind. The future remains unwritten, but the legacy of these changes is etched into the very fabric of Earth. The question that lingers is not only what has been altered, but what will endure. Long before the first footfall of mammals or the shadows of dinosaurs, another life form quietly seized control of Earth's surface. The story of plants is one of relentless innovation, a green kingdom that transforms stone into soil, air into food, and sunlight into life. In the silence of the ancient world, the earliest plants emerged along stony shorelines, their simple forms clinging to damp rocks. These pioneers, small and unassuming, began the slow conquest of land. With each generation, they developed new strategies: waxy coatings to resist desiccation, roots to anchor and draw water from the earth, and vascular tissues to move nutrients skyward. The Devonian period marked a revolution. Ancient forests of towering club mosses, horsetails, and ferns rose over the land, casting the first deep shade. Their roots broke rock into fertile soil, while fallen leaves built up layers of peat. These plants altered the atmosphere itself, drawing down carbon dioxide and enriching the air with oxygen. The world's climate cooled, paving the way for new evolutionary experiments. Plants became architects of ecosystems, Their leaves provided food for the first land-dwelling arthropods and early vertebrates. Their dense canopies shaped humidity and temperature below, creating microhabitats for countless creatures. In the Carboniferous swamps, giant tree ferns and lycopsids formed vast coal forests, their remains compressed over eons into the fossil fuels of today. The appearance of seeds brought another leap forward. No longer bound to water for reproduction, seed plants spread across continents, adapting to arid uplands and harsh seasons. Conifers and cycads rose to dominance, their tough needles and armored cones withstanding drought and grazing alike. When flowering plants, angiosperms, finally arrived, they rewrote the rules of life. Their blossoms lured insects, forging ancient alliances that would echo through evolutionary time. Fruits enticed animals, who carried seeds far and wide, accelerating the spread of forests and meadows. The diversity of form exploded, from the vast grasslands that would sustain herds of giants, to the tangled rainforests humming with hidden life. Plants shaped the fate of every other living thing. Their roots stabilized mountainsides, their leaves slowed the wind, and their fallen bodies enriched the earth. They turned barren landscapes into living tapestries, each leaf and stem a testament to adaptation and survival. As eras passed, their green dominance endured, sometimes challenged by catastrophe, always resilient in the face of change. Even as continents shifted and climates swung from ice to fire, the Green Kingdom persisted, evolving new forms and forging new partnerships. Their quiet labor made possible the rise of animals, the flow of rivers, and the breath of every creature that ever lived. The story of plants is written in the very fabric of the world, a silent, ceaseless revolution that continues to shape the destiny of life on Earth. Beneath the green tapestry of life, Earth itself was never still. For hundreds of millions of years, the planet's surface performed a slow and powerful ballet, a relentless movement of continents, shaping the very stage on which life evolved. This is the story of the supercontinents, vast land masses that rose, collided, and broke apart, each cycle rewriting the rules for every living thing. It began deep within the planet, where heat and pressure churned the mantle. Driven by forces we can scarcely imagine, the continents drifted across the globe like ancient rafts. Sometimes they converged, fusing into supercontinents, giant landmasses such as Rodinia, Pannotia, and the most famous of all, Pangaea. Other times they fractured, sending continents spinning into new orbits. Each assembly and breakup brought profound change. When continents collided, towering mountain ranges rose, vast chains that altered wind and rain, casting rain shadows and redirecting rivers. When they drifted apart, new oceans opened, reshaping climates and isolating populations. The rise of supercontinents brought dry interiors and harsh deserts, while their breakup flooded the land with shallow seas, birthing rich coastal habitats. These slow-motion cataclysms drove the engine of evolution. Species separated by shifting seas followed their own paths, adapting to new climates and landscapes. Plants and animals thrived or vanished, depending on how well they weathered the upheaval. Mass extinctions often followed the most dramatic changes as ecosystems collapsed and new ones emerged from the ruins. Pangaea, Earth's last great supercontinent, was both a cradle and a crucible, its vast interior baked under arid skies, while its coasts teemed with life. When Pangaea began to split, it set the stage for the age of dinosaurs and the eventual rise of mammals. The legacy of these ancient movements is written in the rocks and fossils beneath our feet, a record of continents forever in motion. The dance of continents is not over. Even now, plates drift and mountains rise, shaping the world of tomorrow. The restless Earth ensures that life will always face new challenges and new opportunities in the endless cycle of creation and change. High above the shifting continents, a new frontier beckoned, one that would forever change the destiny of life on Earth. Flight. the power to defy gravity, to soar where few had ventured before. But this remarkable ability did not appear overnight. It was the result of countless tiny steps, forged by evolution across millions of years, and a dizzying array of creatures. The first pioneers of the sky were insects. In the ancient swamps of the Carboniferous period, dragonflies with wingspans as wide as a hawk's glided over fern forests. Their secret lay in slender, jointed wings, delicate membranes supported by intricate veins, powered by strong muscles anchored to their armored bodies. These early aviators mastered the art of maneuvering, hovering, and darting through the air, escaping predators and seeking new food sources. The evolution of flight in insects unlocked whole new ecosystems, sparking an explosion of diversity. But insects were not alone for long. As the continents continued to shift, another group of creatures looked skyward: reptiles. During the age of dinosaurs, some reptiles took to the air in spectacular fashion. The pterosaurs, with wingspans ranging from sparrow size to over 10 meters, ruled the prehistoric skies. Their wings were a marvel of engineering, thin membranes of skin stretched between elongated fingers and their bodies, light yet strong. Some soared on rising air currents over ancient seas, while others flapped powerfully through dense forests, hunting fish or snatching prey from the ground. Then a new lineage emerged: the earliest birds. Descended from small feathered dinosaurs, these creatures developed a revolutionary adaptation: true feathers. What began as simple filaments for warmth and display gradually became complex structures, perfect for flight. Over generations, arms transformed into wings, bones became lighter and hollow, and tails shortened for better balance. Archaeopteryx, one of the earliest known birds, combined sharp teeth and claws with wings covered in flight feathers, a living mosaic of past and future. With each innovation, the sky became more crowded, more competitive, and more alive. Flight offered escape from predators, access to new food, and the chance to travel vast distances. It demanded new senses, sharper vision, and faster reflexes. For those who mastered it, the rewards were immense. From shimmering dragonflies to soaring pterosaurs and the first birds, the evolution of flight reshaped life on Earth. It allowed creatures to transcend their earthly bounds, turning the sky into a new world of endless possibility. Beneath the tranquil forests and ancient seas, another force was at work, one both creative and destructive. Deep within the earth, molten rock churned and pressed against the crust, searching for a way out. When it found a weakness, the world above was forever changed. Welcome to the age of ancient volcanoes. Across the planet, colossal eruptions ripped through the landscape, spewing rivers of lava and clouds of ash into the sky. These were no ordinary eruptions. In places like what is now Siberia and India, volcanic events unleashed fire over millions of square kilometers, vast flood basalts that shaped entire continents. With each eruption, the land was buried under thick sheets of cooling rock, sculpting towering plateaus and splitting apart the world's surface. But the story didn't end with the land. Volcanic ash, rich in minerals, drifted on the wind, settling far from its source. It fertilized ancient soils, nourishing forests and swamps, and providing a foundation for new ecosystems to flourish. Yet these gifts came with a cost. The gases released by these eruptions, carbon dioxide and sulfur dioxide, transformed the atmosphere. Sometimes they warmed the planet, triggering greenhouse effects that turned lush landscapes into deserts. Other times, sunlight was blocked by ash and aerosols, plunging the world into sudden, chilling darkness. These climatic shocks could last for years, challenging every form of life. Some of the greatest extinctions in Earth's history were linked to these volcanic cataclysms. Entire lineages vanished, unable to adapt to the rapid changes. But from the ashes, survivors emerged, hardier, more adaptable, ready to seize new opportunities in a world reshaped by fire. Volcanoes also seeded the world with new land. Islands rose from the sea, mountains towered above plains, and deep rifts split continents apart. Over millions of years, these fiery forces carved the face of the planet, creating the raw, dramatic landscapes that would one day host forests, rivers, and the footsteps of ancient creatures. In the grand story of life, volcanoes were both destroyer and creator, reminding us that even in the darkest eruptions, the seeds of new beginnings are sown. Long before mammals roamed the plains or birds soared through ancient skies, a quieter revolution unfolded in the world's rivers, lakes, and swamps. These prehistoric freshwater ecosystems became cradles of innovation, laboratories where life experimented with new forms, behaviors, and alliances. The earliest freshwater habitats were born from shifting tectonic plates and receding seas, their basins filled by rainfall and runoff. In these new worlds, the rules were different. Unlike the vast, salty oceans, freshwater bodies were ever-changing, expanding, shrinking, and sometimes vanishing altogether with the seasons or shifting climates. Within these unpredictable environments, life flourished in unexpected ways. Ancient fish, like the armored placoderms, patrolled the murky shallows, their bony plates both shield and weapon. Alongside them, lungfish developed the remarkable ability to breathe air, an adaptation that let them survive even when drought turned rivers to mud. Strange amphibians, some as large as crocodiles, lurked at the water's edge. Their sprawling limbs and powerful jaws made them both hunters and hunted in a web of life that included giant predatory insects, early mollusks, and swarms of tiny crustaceans. Here, dragonflies the size of seagulls zipped above lily pads, while beneath the surface, trilobites and early shrimp-like creatures sifted through silt for food. The plants, too, evolved to meet the challenges of freshwater living. Towering horsetails and dense mats of club mosses anchored the banks, their tangled roots stabilizing soil and filtering water. Algae and primitive ferns spread across the shallows, creating floating green carpets that provided shelter for eggs, larvae, and the smallest of swimmers. But these ecosystems were fragile. A shifting climate could dry up a lake, strand its inhabitants, or flood the land, sweeping away entire communities. When volcanoes erupted or continents drifted, rivers changed course and new lakes formed, forcing life to adapt, migrate, or perish. Despite these challenges, the freshwater world became a vital engine of evolution. Here, the first four-legged vertebrates, ancestors of all amphibians, reptiles, and mammals, took their tentative steps onto land. Predator and prey, plant and animal, each played their part in a complex dance that shaped the future of life on Earth. In the story of our planet, the rise of these prehistoric rivers and lakes was more than a backdrop. It was a turning point, a place where the possibilities of life flowed ever onward, shaping the destiny of all who would come after. In the ancient world, survival was a game of senses, a silent contest played out over millennia as the first animals learned to see, hear, feel, and even think in ways never before imagined. The evolution of senses was not just about detecting danger or finding food. It was about unlocking new worlds of experience, and with them, new strategies for survival. In the murky depths where light barely reached, the armored placoderms developed pressure-sensitive pits along their jaws, allowing them to hunt by detecting the faintest ripple from hidden prey. Meanwhile, in clearer waters, the eyes of ancient fish grew larger and more sophisticated, granting them the ability to spot predators and navigate complex environments. On land, early amphibians faced new challenges. Their eyes migrated to the tops of their heads, perfect for watching above the waterline, while their skin became sensitive to the touch of air, alerting them to the presence of both friend and foe. Some, like the labyrinthodonts, evolved complex hearing structures, tiny bones that carried sound waves from the ground and water to their inner ears, letting them sense the approach of danger long before it could be seen. But it wasn't just about sharper senses. In the tangled undergrowth, early reptiles began to experiment with a new form of awareness, intelligence. Simple brains grew larger and more complex, allowing these creatures to remember safe hiding places, recognize rivals, and even anticipate the movements of their prey. The first signs of problem-solving appeared, an animal using a stick to probe the mud for insects, or learning to avoid a poisonous plant after a single bitter taste. Some predators, like the ancient synapsids, developed keen night vision and a heightened sense of smell, tracking prey under the cover of darkness. Others relied on camouflage, blending seamlessly with their surroundings, or on mimicry, imitating the warning colors and shapes of more dangerous species. Communication, too, began to evolve. The croaks and chirps of early amphibians carried messages across swamps and rivers, warnings, invitations, or simple declarations of territory. Chemical signals drifted through the water, marking trails, attracting mates, or repelling rivals. Every sense, every spark of intelligence was honed by the challenges of prehistoric life. In a world where the rules changed with every drought or flood, adaptability became the ultimate survival skill. The animals that could sense more, understand more, and respond faster were the ones that thrived. In this hidden arms race of perception and awareness, the stage was set for even greater leaps to come. The story of life on Earth would never be the same. At the edges of the ancient world, where the sun would vanish for months and ice ruled the land, life faced its greatest test, the prehistoric polar regions. These were realms of extremes, where summer brought endless daylight and winters plunged the world into darkness. Yet even here, evolution found a way. The polar continents, drifting through deep time, were not always frozen wastelands. During the age of dinosaurs, lush forests blanketed the Antarctic and Arctic, fed by the brief but intense summer sun. Towering conifers and ferns, some as tall as modern apartment buildings, formed dense canopies that sheltered an astonishing array of life. Here, herds of polar dinosaurs roamed. Some, like the small, swift Leaelinosaura, grew enormous eyes, perfect for gathering the faintest light during the months-long twilight. Others, such as the burrowing polar hypsilophodonts, dug deep into the earth to escape the bitter cold, emerging only when the air grew warm enough to support life above ground. The climate demanded more than just warm blood. Some ancient reptiles and amphibians developed anti-freeze-like proteins in their blood, preventing ice crystals from forming inside their bodies. In the icy rivers, prehistoric fish like notothenoids evolved similar adaptations, gliding through water just above freezing, while the world above slept beneath snow. Seasonal cycles drove dramatic changes. Plants dropped their leaves or entered dormancy, storing energy to survive the long dark. In spring, when the sun returned, entire forests would burst into life almost overnight, feeding a frenzy of growth and reproduction before the next winter's shadow fell. But life here was a gamble. Floods from melting ice, unpredictable food supplies, and predators lurking in perpetual dusk meant every adaptation was tested to its limit. Only the most flexible species survived, those that could hibernate, migrate, or simply wait, patient and silent, for the world to turn again. In the prehistoric polar regions, life was a masterclass in resilience. Each creature, plant and microbe was a testament to nature's relentless drive to adapt, endure, and thrive, even at the very edge of possibility. As the sun dipped below the horizon and darkness swept across the ancient earth, a new world awakened, the realm of the prehistoric night. While daylight belonged to the giants and crowds, the cover of darkness offered a different kind of opportunity. Here, the rules of survival changed, and evolution favored creatures that could master the shadows. In these primeval nights, some of the earliest nocturnal animals emerged. Tiny, mammal-like reptiles, shrouded in fur, scurried through the undergrowth, their senses finely tuned to a world without light. Enlarged eyes, packed with rod cells, captured every glimmer of moonlight, while sensitive whiskers probed for movement in the leaf litter. These pioneers of the night learned to listen, smell, and feel their way through the darkness, avoiding the prying eyes of day-active predators. Predators, too, adapted to the night. Ancient crocodilomorphs and small theropod dinosaurs quietly stalked their prey, relying on acute hearing and a subtle sense of vibration through the ground. Some, like the feathered troodontids, boasted oversized eyes and possibly even the first hints of stereoscopic vision, giving them a three-dimensional view of their twilight world. But night was not just for hunters. Insects, the true architects of darkness, evolved bioluminescence, tiny bodies lighting up to signal mates or warning of danger. Firefly-like beetles pulsed through ancient forests, their glow painting the shadows with fleeting patterns. Moths developed scales that scattered sound, evading the echolocation of early bat-like flyers, while frogs and small amphibians sang complex songs, their calls echoing through the cool, humid air. Darkness itself became a driving force in evolution. Prehistoric plants adapted to pollinators that worked by night, opening flowers only after dusk and producing scents that traveled farther in the cooler air. Some fungi, thriving in perpetual gloom, developed spore-releasing mechanisms triggered by the faintest vibrations of passing feet. Life in the night demanded more than camouflage. It required innovation. Some ancient fish, navigating pitch-black rivers and lakes, developed electroreception to sense the faint electric fields of prey and predators alike. Others, like the early squamates, evolved heat-sensitive pits, allowing them to see the warmth of other animals in total darkness. For millions of years, the prehistoric night was a laboratory of adaptation. Those who embraced the darkness found new ways to thrive, carving out niches untouched by the sun. The legacy of these nocturnal pioneers endures, shaping the senses and behaviors of countless species that still walk, fly, and crawl beneath the stars today. In the intricate web of prehistoric life, survival was rarely a solo endeavor. Long before the first flowers bloomed or the first mammals scurried through the undergrowth, ancient organisms were already forging alliances, some harmonious, others one-sided, and a few downright ruthless. These relationships, known as symbioses, became vital threads in the evolutionary tapestry of Earth. Mutualism, the art of cooperation, blossomed in the earliest oceans. Primitive corals formed living reefs by partnering with photosynthetic algae. The tiny algae captured sunlight and produced food, nourishing their coral hosts. In return, the corals provided shelter and access to sunlight, building vast underwater cities that supported entire ecosystems. On land, towering tree ferns and cycades formed alliances with fungi, their roots entwined in a silent agreement. The fungi delivered water and minerals, while the plants fed them sugars, allowing both to thrive in harsh, nutrient-poor soils. Commensalism, the gentle art of taking without harm, emerged in many subtle forms. Within the fronds of ancient horsetails and club mosses, small arthropods found refuge, shielded from predators and the elements. The plants, indifferent to these tiny tenants, continued their slow ascent toward the sun. Elsewhere, shell-dwelling worms and crustaceans colonized the backs of prehistoric ammonites, hitching rides across the ancient seas, expanding their range without burdening their mobile hosts. Parasitism, the shadowy side of symbiosis, also found its place. Jawless lampreys latched onto armored fish, feeding on their blood in a relentless struggle for survival. Ancient ticks and mites burrowed into the scales of reptiles, extracting sustenance drop by drop. Even plants joined the fray. Some early seed ferns sent out root-like structures to siphon nutrients from their neighbors, thriving at their expense. These bonds, whether beneficial, benign, or exploitative, shaped the course of evolution. Mutualists flourished together, their fates intertwined. Commensals found opportunity in the presence of others, while parasites drove their hosts to develop new defenses. Over millions of years, the push and pull of symbiosis wove a complex network of dependencies, fueling innovation and diversity across land, sea, and sky. In the prehistoric world, every life was linked to another. The story of symbiosis is a story of connection, a reminder that even in the oldest chapters of Earth's history, survival often meant finding a partner, an ally, or sometimes an uninvited guest. Long before the first bird soared or insect wings fluttered, the skies above ancient Earth were alive with drama and change. In these prehistoric eons, the atmosphere was both a guardian and a sculptor, shaping the destinies of the land and the creatures below. Imagine the Carboniferous period. Over 300 million years ago, dense, humid air hung heavy above endless forests of giant club mosses and tree ferns. With oxygen levels far higher than today, wildfires would flash through the undergrowth with terrifying speed, ignited by lightning that split the sky. Thunderstorms, swollen by the planet's warmth and moisture, unleashed torrents of rain that carved new rivers and fed vast swamps, cradles for amphibians and the earliest reptiles. Further back, in the time of the great supercontinent Pangaea, the weather turned fierce and unpredictable. With so much land gathered in one place, monsoons swept across arid interiors, bringing brief, life-giving rains to deserts that stretched for thousands of miles. Winds howled across open plains, carrying dust and seeds to distant horizons, spreading life, but also stripping soil and shaping rocks into strange, wind-worn sculptures. The skies were not always blue. Volcanic eruptions could shroud the world in ash, turning day to twilight for months or even years. Acid rain fell, reshaping forests and poisoning lakes. Yet, these catastrophes also cleared the way for new life to emerge, opening niches for survivors and newcomers alike. Clouds, too, held power. In the warm, shallow seas of the Ordovician, thick fogs rolled in from the ocean, blanketing the coasts and keeping temperatures mild, perfect for the explosion of marine life below. At the poles, the low sun cast long shadows through icy mists, while auroras flickered silently above, unseen by any eye, but no less beautiful for their solitude. The prehistoric skies were ever-changing, a canvas of wind and water, fire and light. Their moods shaped the land, tested the resilience of species, and set the stage for every evolutionary drama. Above the ancient world, weather was a force of creation and destruction, a reminder that sometimes the greatest stories unfold not just on the ground, but in the endless expanse above.